Welcome everyone to day 2 of the Hypermatrix workshop. I'm delighted to be introducing Liubov. Nicholas Bear is behind me. He'll be speaking later. And without further ado, because we are really a bit tight on time, let's go on with the first talk from Liubov. Take it away.
So I'm Liubov. I am part of the several laboratories here in Paris, in Balats, LPI, for Macri, and also I was for some time lecturing at PT Moscow, and I see also some people connecting from there. It's great, very international crowd of people. And I will talk about some topic which we have been working on together with several people, which started actually essentially as a research project on studying the knowledge maps and mapping and embeddings, very fancy kind of trendy topics, sorry, not fancy. And my hope here would be that we can also maybe formalize later some in a more mathematical questions of these problems, because there are some areas there that are connected directly to hypergraph topics. And so essentially there will be 2 parts of the talk. I hope we will get back to the second part, because yesterday we had more talks by Richard and by Victor, yes. And beautiful talks also on the topic of non-associative algebraic structures. And I will hope that we may arrive there, but honestly already in the first part, where I will present how these hypergraph structures may help to encode these multidimensional data structures. That would be also already kind of good enough to talk about that. And so before we dive into that, I wanted to actually show this funny example that I've looked at recently when we met with Carlos a year ago, and he told me about this beautiful topic of arity structures, and I was like, it reminds me a lot of things that I have been facing in my research path. And a long time ago, I was part of this Chomsky's bridge of mathematical linguistic team in university, where we were doing linguistic expeditions, and we were analyzing. At that time, it was not called parsing language, but essentially it was parsing language. We were decoding language structures and trying to build grammars. And these formal grammars, they essentially had these beautiful arity structures, which Chomsky in generative linguistics created. So the beautiful thing here was that this structure, this Yoklab Aldibara, was formed as an arity language structure. Because in some languages, from Turkish languages, they have incredibly rich structure where you have not only verbs like have or be that can be attached to the verb, but they also can have some other semantic structures. So the basically semantic of some complex structures, they can actually create new meaning. So they are very arity, and that's something that is fascinating. That will be also related to the topic of the talk. And essentially how I write and why I decided to share it with you was because of 2 things. In 2023, we published a paper about hypergraph knowledge mapping, where we tried to map millions of papers and do it with kind of an embedding. I will explain what embedding is, but essentially what we were trying to do was to convince everyone that in order to construct some kind of knowledge map from all published materials on, for example, some topic in archive, like for example, Nick publishes his rewriting paper in mathematics and in high energy physics, and I publish it in other subjects, and how this overall progresses the science. So that essentially that was a question, and we were trying to study that. And reviewers, for I think the first time in my life, asked really questions which I was not able to answer, and it actually led me to another research. And in SEM here, I put this kind of link also here. We started to discuss why and how by finding matrix of embedding of this knowledge landscape, we could potentially find a proper distant matrix between two data points, which essentially are not embedded in any space, Euclidean space, or we don't know where it's embedded, because data, when people talk now about data, they sometimes do not formalize it, and the word data is kind of ill-defined. So that's just kind of a preamble of this talk, and essentially how it first time it arrived, like 5 years ago when we started to discuss it with Mark, was that we were trying to map a trajectory of a scientist. When scientists start, for example, their path from theoretical physics and then they end up to do study in epidemiology, we essentially wanted to understand whether we could visualize it and kind of do this visualization of science, but not in the way, and study this using theoretical concepts of studying trajectories, right? Like people do here in LPTMC a lot, by mapping this. And state of the art of such algorithms, surprisingly, are very low order algorithms. What I mean by that is that when you map, for example, data, for example, here you see the map that was done by projecting high-dimensional textual data. Well, let's say high-dimensional because you, for example, download Wikipedia and all the Wikipedia articles. And what NLP algorithms usually do, that they assume that these data points are all part of Euclidean space. And then you can somehow, either using either Stisny or UMAP algorithm, you project them into low dimensions. Why you do that? Because you need to reduce what they call redundancy, right? Because typically you first start with a very high dimensional space, right? All Wikipedia articles, for example, right? Or with all these articles in archive. And then essentially when you project them, you apply this kind of relational aspect of 2 points in these high dimensions that will be binary, essentially. Usually there is a big assumption, and there are also many tools for analysis are also essentially very limited to, if you look at these papers on mapper algorithm, which is state of the art of this kind of projection embedding spaces, they're very binary. But then when I started to read more about many other things, then I found out that there were not many ones which would be taken into account the fact that some of these structures, or like structures that I showed in the beginning in the language, or structures in science, they essentially are not having just this binary aspect, that they can be kind of not two-dimensional and essentially not even three-dimensional, but n-dimensional kind of, yeah, they can be very complex. And then afterwards, also when discussing with other people more, I realized that essentially there are already attempts of people trying to understand when to use high order structures and when not to use. So in this graph, maybe Francesco will talk today at the end a bit more. Essentially, it's kind of semi-supervised algorithm that can be built on top of that, where if we have some high order structure, like coming from biology or technical system, if the number of high order motifs is high enough, like in some kind of these hypergraphs, then you do need to apply some tools and statistical and like the algebraic mathematical tools that will be high order. But for some cases, we will not need them because they are just really low number of these high order motifs. Like basically, if you will apply essentially very complex rewriting systems there, maybe you will learn something, but essentially they are very higher, not really high order. And so that's one thing. And also later on, Kostya also shared very interesting research they were doing also on topology of cognitive maps, and where they also find this kind of high order structures, but how to study them. Sometimes people actually understand that there are not many ways people studying them. And so essentially, I want to get a bit more concrete on what we will talk about here and what are exactly kind of these data structures that we can essentially, and how we can apply this higher level idea that we need to study data using, I mean, in some cases, right? In some cases, what I mean by some cases is when you really do have some, so in this plot, which I'm hiding behind, there were paper where they were studying motifs in higher order structures, and motifs in high order structures, they were trying to show the number of high order structures motifs in some specific hypergraphs, right? And in some hypergraphs, they were very present. So how do we decide, right, in the algorithm that you will need to basically apply that, or like systematically find them? So the idea of the algorithm that we are now working on also with one of my students, and we try to kind of more formalize it, and I will explain a bit more the context here, was that if you first find a way to, like, you start with some data, and essentially data is very ill-defined object. I mean, it's not the data which Nick kind of you define later on, so I want to make sure that it's not confused with other ones. Then afterwards, you transform it into some other structure, high order structure, essentially. And then afterwards, you can also go, essentially, usually now algorithm, depending on which algorithm you use, for studying, or what's it called, learning features, right? Features learning algorithms, you just assume a lot of things about the data. You assume, for example, that there is a manifold that can be locally connected. That is already a big assumption. Then you also assume, and this is, I'm talking about UMAP, for example, one of these algorithms. Then afterwards, you assume that there is already a structure that it's essentially, in the case of UMAP algorithm, probably some of you already know the UMAP algorithm that actually essentially tries to learn from your high dimensional data points. So we start from the left to the right, your analysis, and you essentially first, for example, you start with articles, which are data points in your high dimensional space. And you want to learn what are the patterns in these structures, right? Essentially, that's what many people do in topological data analysis, if you look at these publications. But the problem, which we will talk about today here, will be that essentially, first of all, the assumption of this manifold learning sometimes for some data structures is very strong. That essentially the local connectedness of the manifold that you want to learn from the data sometimes is very strong, and it's not true simply. We can talk about this for some benchmark data, which we tried to look at. And then afterwards, that's also, there is something in between the manifold and the data for which actually maybe these assumptions will not need to be taken, but we do have some methods for analysis. And second thing, which also I was not mentioning so much here, but that there is also hyperparameters for this embedding algorithm, that actually there is not just one method that you apply, but actually a set of methods. And nobody actually can tell which parameters, like it's hyperparameter sets. And to make it even more complex, now people actually do apply some autoencoder models, right, for doing the same thing. So they don't do just manifold learning or stochastic embedding, what they call, right, Tisny referred to that, but they actually apply some more complex architectures. Then they basically project it into some latent space. It's essentially these data structures are projected into the latent space of embedding methods. And then hoping that this latent space makes sense, you actually can afterwards what they call decode the information, and then afterwards kind of, for example, either in the case of models which project or generate structures, they can generate or generalize these structures and decode these methods into generating, for example, content. But there were recent papers that tried to look at the structure of the latent space that were saying that In fact, right now, these hyperparameters sets for these such models, they need to be somehow found, and there needs to be a very solid algorithm. By solid, I mean that they're often optimized through assumptions that if you have, for example, for the case of UMAP algorithm, the way how it works is that in UMAP you're assuming that number of neighbors needs to be neighbors of the points, if you project your data points, needs to be small in case of the assumption that your data is sparse and high enough, like higher, like it's very empirical. Basically, you need to get a sense out of that. And so on benchmarks data, for example, this algorithm may work in a very, very specific way. So they may work, for example, getting, so what you will essentially do if you, for example, project concentric circles into UMAP. So UMAP will kind of transform your data, will remove noise, and then afterwards you also ask algorithm to put into the hyper edge nodes which are connected within the circle of certain radius. What you will essentially get, you will get two circles, but they're somehow twisted, and that topologically will be equivalent to circles, but essentially you see that this, what we call topologically learned structure by the algorithm and circles themselves, right? They're essentially two objects. So essentially what would be nice to have is a set of measures or invariance measures on this for applied for the right structure, that when we deal with some really complex data, like from whatever, brain cancer, some very difficult structures where we don't know ground truth, that we would be knowing what we are doing. So the idea behind this work that we were continuing to do was that we wanted to test it on very simple benchmark data sets, which exist, to show that how it works here. And also just to show it on the example that I've started to show you, that the way how we do that is that we have some data set, right, which we are encoding using specific coding scheme that, for example, in the case of hypergraph for archive data set, we have an edge, a hyper edge that is encoded as the paper. So paper consists of several set of nodes, which are scientific fields, right? Statistical mechanics, computational geometry, machine learning, and a hyper edge will be a paper. So we basically construct a hypergraph from that, and then we can ask certain questions, right? How is it embedded? What would be the graphical structure? How would it characterize, for example, emergence of scientific fields in this case? And what would be the distances distributions in this higher order structure, right? And how would it be different? Would it be actually useful, first of all, to represent this data set as this structure, first of all, because actually we may not need, as if you remember Lotito's plot that I showed you in the beginning, it may not always be useful to represent it in the structure. And maybe I go too fast if you have any questions of this construction of this data set, but I think it's okay. Right. Okay. So, and we studied this in several papers. We studied projecting mechanisms of such a data set from different perspectives already. We studied it from the perspective of embedding it into a manifold. And right now we wanted to go step back, basically staying at this level of this hypergraph projected structure, in order to kind of pause for a second this structure and just to see whether we would be able to learn the same amount of information from this as we would be learning from projecting it on the manifold. And essentially, that is also a general question that people ask when they use any of these embedding methods, that they try to understand whether projecting, or kind of what physicists often refer to as cross-graining, whether you would have the same amount of information that you can learn from this projected structure as from the projected structure in a different way, right? And also which algebraic properties of these hypergraphs you may want to study and highlight here. So I'm talking about here very kind of high level maybe structures, but the idea is actually also to show here the very specific. So because the graph is very messy, it will not make sense to visualize and look at it. So we, of course, would need to do some level of apply some measures. That's typically what hypergraph community of people doing. And from previous research, we already saw some structures in such a cotag hypergraph or cotag network in this case, which is cotag projection of the hypergraph. So in this case, right, in this case, we constructed a hypergraph by encoding nodes as fields, and hyperedges would be papers. And in this case, we encoded an edge if there is a binary relation and there is certain number of articles in both fields, right? So it's kind of a projection of this hypergraph. And there would be already some sort of a reconstructed knowledge space and reconstructed information from that. But essentially, as we saw also from the paper on motifs in hypergraphs, that in the case of co-authorships networks, also in the hypergraph networks, our hypergraph network falls exactly on this one where the number of scientific fields, and I don't show it here, but I show it in the paper, that there is on average number or average arity of a hyperedge is higher than 3. So our graph would essentially, our hypergraph will fall essentially to this one, right? Where arity basically of an edge would be higher. So essentially it would be this one and not the other one. So that's why, I mean, that was a motivation for us to come and ask, how can we study this high order zoo of structures? And also, second question, which I also started to ask with people like Kostya and his collaborators from MIPT, how, in which cases low order measures still would be applicable, because quite often they lead to misleading cutting of the or simplification, oversimplification of such results. And so if it depends, and in a way it will, the answer to this question depends on to which community of people you will talk to. Because, you know, if you'll come to people from rewriting community like Nicholas Burr and, you know, people like Carlos, they will tell like, you need to apply rewriting. And if you will need to, you'll come to people from, from maybe people who are more in the graph community, that will of course tell you, oh, you need to apply the generalized Laplacian and analyze the structure, but essentially they are cutting the structure of a graph essentially, and they're simplifying that, right? So there is no universal answer to that question. And the paper which I really liked on that, so to answer these two questions of, okay, now we constructed this graph and we saw that it definitely has some hierarchy structure in it, as I showed you statistically speaking. So which methods should I use? And essentially, as we discussed also with Kostya, we maybe discuss later on, there are of course some path analysis, right, and which comes more from differential geometry that you can apply there to study this high order structure in knowledge graph. But essentially, you may not it may not be necessarily very easy to do it, and I will show you why. So first proposition here would be that we would need to first define the hypergraph metric structure such that there would be some inherited structures and properties of such projections. What I mean by that we construct a hypergraph, and we construct it from data essentially. In this case, for example, it's a knowledge hypergraph from archive papers, right, H. And we we impose a metric on it. Metric, by metric, I mean a distance, a notion of a distance, which can be defined through a line graph that is well-studied structure, or through a click graph. And essentially we project, or like we define a metric, and people from Wolfram Institute discussed it beautifully. And there are people who are kind of using, and they are creating a sense of knowledge, kind of, there is a knowledge already on this field of how to define a metric on a hypergraph. But what if we then afterwards project this hypergraph? Because there are, as we will show, we will probably see also from Nicolas' talk tonight, there are some situations when already make algorithms running on graphs, just graphs themselves, they can already be very complex to calculate. So sometimes it's inevitable to project these structures, right, into graph structures. And so in some cases, we would need to be, in this case, in this realm, right? We need to use and study only projected versions. So in which cases metric introduced on that structures would actually be making sense in that give you the same results as a metric on the introduced on the hypergraph. And a second way and a second proposition that I wanted to discuss with you was this idea of encoding hypergraphs as algebraic structures, which we discussed a bit with Ward, who couldn't come today, unfortunately. But there is this crowd of people who discussed and developed what they call non-associative Bernstein algebras, which essentially encode your graph structures. In case of graph, right? I'm not talking about hypergraphs, graphs here. They encode them as a certain algebraic structures as a direct sum of U and Z, defined as a set of all pairs introduced for each edge, where you would have two vector fields, which would be taken from the set of nodes and set of edges, and that would be introduced on edges and nodes for graph. And essentially, I haven't found yet the generalization of the dimensional algebras for hypergraphs yet, but you can extend it at least for ternary hypergraphs. So the ones where you have ternary edges, and essentially this hypergraph, graph Bernstein algebras are used or have been used by physics mathematical community to encode them for studying isomorphism properties of graphs. So the idea, and I think that I wanted to discuss with you, but I don't have so much time, I think, was to understand whether these structures would be essentially valuable structures for encoding hypergraphs. And this is an open question, which I don't really have yet an answer. Only kind of the sense that you can pretty much everything that you know is true for Bernstein algebras for graphs encoding. May actually also be extended to some extent to this ternary, the graphs, hypergraphs only with ternary edges, hyperedges, sorry. Essentially, it's only because of this commutable multiplication, which you can extend it, which by the way, Richard, I need to show you because it's very similar to what you were showing yesterday at the talk. But yeah, and finally, maybe, it's not finally, but hypergraphs, which we talked about before, and it's something that I needed to also thank Rygarodzki, also people to point out this paper where, there is ways to project, of course, and encode. I don't like the word projection here in the sense because you are encoding the hypergraph representation as a bipartite or click or line graph. A line graph is a structure where you encode a hyperedge as this triploid, actually, Richard. I didn't hear from people the word triploid, but essentially triploid in the case of hyperedge would be an edge that you substitute by a node in the center of the hyperedge. So that would be an analogy. And line graph is a graph where you substitute an edge with a point here in the center, and then afterwards you want to count a path, make a path on the hypergraph. You substitute it by a path in such a line graph, and that would be one of these representation of a graph. And essentially what we were calculating and estimating and then comparing to the people from Vasilyeva and people who were studying kind of benchmark data of hypergraphs versus line graph projections. They were comparing, and I was trying to do the same for knowledge graph. What they were trying to compare was this difference between weighted hypergraph distance and distance in a click projection. And so interesting thing was that the number of nodes pairs of the differences of the nodes pairs, like there are 51,000 of 576 pairs, which would be giving you from 0 to 33% of the difference. So there were basically very small number of differences of dyadic kind of pairs. For some specific hypergraphs, you don't really care so much whether you treat them, as I showed you, as a hypergraph structures. But for some, I think this one was this structures from hypergraph. I need to see exactly the name, Enron email hypergraph, where it would actually, they would make a difference, like there were social networks versus the email network structures, where there would be a big difference how we define it. The matrix structure on a hypergraph, and the line graph distance, which people typically are okay with calculating, would lead you to some other response rather than the click projection. I mean, click projection, I didn't define it, but click projection is essentially when you are just counting the hyper ratio substitute by the node. Right, so I can refer to the paper maybe from the MIPT group, where they calculated it for other benchmark data. And for me, I got essentially big differences on the hypergraph structure constructed for edges as hyper edges as clicks or line graphs. And essentially also for comparing these graphs, hypergraphs metrics versus graph metrics, one can always try to find other ways of estimating the differences between these two objects and not use this kind of cruel projections that sometimes lead to really big differences, like in the case of projections of the click versus non-click projections, but like basically you need to be very careful with projections. That was the message. And so, yeah, I don't want to rush, but I want to have time a bit maybe to discuss. So generally, there are many methods where right now people, indeed, we're seeing that sometimes we are applying very, very dyadic and binary logic to this high order motifs presence structures. That can also lead to the development of new algorithms, also where we find where this can be structures, where these algorithms need to be applied, not in every case. And for this, we need to also know which matrix structures which we need to encode. And with this, I want to finish, I think, and to open the floor for questions.
All right, thank you very much, Liubov. Any questions?
Yeah, sure. First of all, Luba, thank you very much for your speech. It was really great and very artistic. I wanted to ask you about the Gromov-Hausdorff distances you mentioned in the last slide about the cookbook. Gromov-Hausdorff distance require building some manifold to embed your data structure into. And if it's a hypergraph thing, it means that it's kind of hierarchical, and it might have some complex inner structure. So it's a very hard question for me personally. How do you define this manifold? I found Basser theory interesting for these things, but what do you think about it? And what can you give a detailed recipe of this page of your cookbook, if it's okay? Thank you.
Thanks, Kostya. Yeah, actually, so after I was trying to discuss with some people from Balazs a lot on this topic, because there were a lot of people who were applying, I don't know, autoencoder for working with a lot of data structures, just to try to, for example, encode the amount of information and then, right, to project that and to do it not using some kind of very like basically hyperparameters, right? And these models, for example, can be huge. And so you want to have an algorithm for finding these hyperparameters. And there was this discussion that, oh, maybe we can actually first try to decode the structure, which would be not a manifold like, but somehow learn a hypergraph, how to construct a hypergraph. I mean, it's also a question, how do you construct a hypergraph for that? But essentially the topic came out to talk about the topic of the co-optimal transport. I will post maybe this paper from Nurip's people on this hypergraph co-optimal transport, where they were defining this metric properties, and they were claiming in the paper to formalize common methods for transforming a hypergraph into a graph as maps between the space of hypergraphs and the space of graphs, and studying kind of functorial properties of Lipschitz bounds and demonstrating that this hypergraph co-optimal transport would lead for you to be able to compare graphs and hypergraphs in this case, I mean, in our case, for example, right, constructed on the same set of nodes. Because I mean, what I understand from I really know really little, and there are people in the audience, I should not be speaking and answering this question to you, but they may be. You will try to define this, right, Gromov-Hausdorff distance, which I understand that as kind of generalization of their normal distance, right, is that you first have two sets of nodes and you want to compare them somehow. And the way you do is that you start to grow circles, right, from one set until you reach the other nodes, and you kind of generalize it, and the way
make a filtration.
Yeah, exactly. So, and the same was idea to compare, for example, two metric structures introduced on two graphs. And so essentially there was in this Redko et al. From Nurip's 2021 paper, which is essentially a machine learning conference. I have no idea why. They beautifully defined it, these theoretical foundations of studying what they call hypernetwork measures for different, and comparing these metric structures on different hypergraphs. They claimed that that would work there, and I will post it in the chat, this paper. But if you have, because I know that you know more on that, maybe you can answer your ideas on this and your feeling on this paper. I think it was in neural information processing systems paper. I will post it in also streaming. Yeah, because you used it for hypergraphs as well.
I'm trying. Yes.
Yeah. Okay.
Yeah, with my student, we just a couple days ago constructed several hypergraphs from hippocampal activities, and moreover, we have constructed hypernetworks and studied each level statistics, how they interacted, and well, they're weird. We will discuss it quite a bit later. And I wanted to ask you.
Yeah.
I want to ask you about this slide about the knowledge graphs on the archive. Did you find an interesting approaches? Because on this graph, it's obvious that you have some community structures, and there are ways to detect them, like betweenness centrality or something like that. I like geometrical approaches, for example, Ricci flows on these graphs could be very applicable to finding the communities. Did you study, and do you study actually, the community structures separately? Because you got the point, and you say very important things, that globally the graph is, well, its statistics and some invariants are not very well pronounced in terms of distinctions between graphs, but studying their individual community structures, it's subgraph structures, some kernels, rich clubs, is a way to learn it, in my opinion.
The kernel?
Yeah, the kernels of the graphs. And rich clubs, which the neurobiologists call it.
You mean, what do you mean by kernels?
I mean the communities of the nodes who have a high amount of edges and hyper edges growing from them.
Yeah, essentially what we did with this paper, I didn't show these results because I kind of already talked so many times, not so many times, but in the initial paper.
Enough times.
Yeah, I talked sometimes, yes, about this on this in this paper where we looked at what they call cognitive distance between fields. And what we looked at was essentially it was not a matrix that we were introducing there, but essentially after we project, for example, some papers, right? It's 1.5 million papers that we, for example, project here, and what we essentially study was the distance, but not like a metric distance in our case, right, on this manifold, but the graph distance between each fields, right? Because actually, essentially, there were recent claims saying that essentially science kind of becomes one field again, right? It essentially, if you look at it as a window analysis, it will be looking as if it will be becoming more and more connected. So we wanted to test this numerically, quantitatively, right? And the same we wanted to test on the hypergraph level of the representation, but turns out that essentially both hypergraph and binary structures representation, if you define the cognitive distance as a shortest path or number of shortest path in the case of a very cruel definition of it, an unweighted sense, because essentially it can be also weighted, and if it's weighted, then it may change something. If you define it on a unweighted, for example, case, you will see essentially the same things. It doesn't really matter represented as a hypergraph structure or not. But essentially, if you will go maybe to weighted representation of such a hypergraph, then it may change because it will be different. You will need to account for some differences how you encode these hyper edges, for example, and then there will be a small distinction that will lead to differences. I did not test yet it on the weighted case, and also, there are some sort of questions of also which metrics need to be introduced initially, as we discussed in this same meeting, where we discussed what needs to be a metric. Actually, why it's Euclidean? Maybe it's not Euclidean essentially initially.
Maybe it's not a metric.
Yeah. So it's a naive thing to show that it's So in this case, reviewers at us, they were asking us, they were quite good in saying that, in fact, you should not stop there. Even though like really 99% of papers, it's really, really like even not asked, right? So maybe at some point we will find out that indeed maybe it's not a question to be asked.
Yeah, yes, classics say all dissertations are bred, but some are finished. Thank you very much. Very interesting.
Thank you, Kostya, for coming. Thank you.
If you introduce a metric, you can introduce also visuality. Replacing reach down, you can replace edges, not the vertices by faces and faces by vertices.
But metric on the graph or on the hypergraph or?
The spacing which you see hypergraph in the thing.
Yeah.
Embed them in hypergraph. And then it's the question whether you get not all the graphs, but the dimensions.
I don't assume here that it needs to be in. I was not indeed assuming that. Yeah.
Sorry, yes. We're just saying. I don't know what they're still in. It's okay. It's okay.
Because it's coming from the loudspeakers.
Really? Or I should go.
Yeah.
Oh, wait. No.
Yeah. So, yes, we cannot hear the questions from here. So I will just relay. So Richard asked whether once there is a metric, if we can introduce a Hodge duality, and so that was the question. Any other questions from the room here? I have one.
I mean, maybe just potentially a conceptual question. So if I understood correctly, you take a problem like looking at a data set of archived papers. Then there's, of course, a curation step where you decide, okay, I'm going to track for each paper, which keywords does it cite or whatnot. So in computer science, we say you basically make a class structure. You say there's a class of being a paper, and it has fields, which are, and then you decide what data of connectivity you are tracking, or whether it's just having certain sub-properties and so on. But at the end of the day, this would, in the simplest case, give you a bipartite graph without any actual extra encoding step, right? You would basically have the type of, I mean, what is it, a paper, and a type of keywords, of which there are different kinds. Yeah. And then it seems there's no actual encoding step other than your choice of data scheme, giving you then some kind of fancy type graph, right? Not necessarily hypergraph, because just a bipartite graph, which you could transcribe to a hypergraph, of course. But so I didn't quite get the point. The goal you have is apparently that if you have a data set, you want to analyze it, that if you have two nearby, you want to have a notion of nearby data points, so to speak. So the metric property should be that points that are similar are close, or is that, what is the design goal here?
Yeah, so there were several questions, and maybe I didn't dissect them enough to really, like in the beginning, the first part of the talk, I wanted to focus more on this idea. Indeed, if everyone heard the question, but basically the main general question was, why do we sometimes need to care? If I understand well what your question, which type of, for example, metrics or measures we will need to apply on these projections or representations if we are caring about specific encoding, maybe, or can I interpret your question this way? I mean,
it's more like why saying, is it the case, because I'm an expert, that so binary or general separated classes is a lot of metrics, so it's usually for hypergraph or
Yeah, distance.
I think they call it metric.
Yeah.
I think this is a metric thing with.
Yes. That's why. Yeah. That's why it's also confusing. I think the way how I wrote it, because I wrote it more or less that the way how you read kind of metric as you introduce already a metric, but you don't.
Are you trying to construct what's called length space? So you're defining a sample of what things should be close in this notion of length, and then trying to check whether this syntax gives you sufficient properties for length space, or reason that I guess that's have perhaps necessarily manifolds is a little bit too much for us.
It's very good question that you asked, because as you noticed, first of all, as you noticed already, I did not distinguish between the two here, and it's a big problem in general. I think in this research that needs to be kind of every definition kind of needs to be very well defined here. And second, if you have, for example, the click representation, which I shared here, I mean, I didn't share it, reshare the slides, but the click representation and the high order, bipartite representation sometimes will be enough as a representation of a hypergraph, right? So you don't have to go to other representation. Did I understand well your question? Like that sometimes you don't need to go to the.
How you get from the paper, for example, have at least in the high level description. Seem to be automatically a bipartite graph. Basically, the data type you were saying, you have a field of paper, field of words.
Yeah.
That's a bipartite graph by definition, without doing anything. But then it seems that not a little bit about the definitions that you want to somehow do data analysis on these graphs.
And also bipartites would be, you mean that it would be weighted in this case, right? Also, I mean, it can be, and
the basic field.
Yeah.
Is quite visible, but any extra. I mean, the question is how you select what you track of a paper. Of course, that's a certain design choice. But in the end of the day, you want to. I thought that the point of your work is to then be able to maybe officially you want to have some sort of notion of closeness between similar structures.
Sure. Yeah.
Because in chemistry, because of course of machine learning methods, of course, there's similar work on chemical graphs in that case. And there's also been works on random representations that basically make similar structures, also similar in their representations. Some interesting work. Traditionally in chemistry, you call them in line notation, so string, which is somehow capable of coding a kind of code. Recently, there has been work on a new encoding called self-piece, which is optimized so that similar graphical structures are also similar in the textual representation. I'm wondering, is that the goal or honestly?
Wow. Yeah. I mean, essentially, this discussion started from this whole bunch of literature where people were claiming we visualized how science now looks like. Like there were really set of papers. I don't want to put them now because some of them were claiming that science has a cyclic structure. Like people were really posting this. I don't say that it's pseudoscience or something, but it was really interesting that people were posting these embeddings of science papers mapped into like a shape of a sort of certain manifold, and they were saying, oh, now we visualize how science looks like we made a discovery. And so there was an attempt to redefine some methods and to make sure that it's actually not there were no false claims on that, and also to show, because when you embed essentially and when you use encoding with autoencoder models, with whatever models of encoding, I showed also two confusing things maybe here, Nick, because indeed in this case, like the bipartite representation of a paper that we started here was indeed you have a tag and you have a paper. Easy. If you don't have a tag, you usually don't have a tag. Essentially, you have a set of words to a paper, right? So it's essentially all, I mean, we discussed it the first day, there is a finite number, of course, of possible combinations of words in the language. So of course, you can put it this way that it will be a very, very large bipartite graph, essentially, that we need to work on, but it will be too big to work with. So that's why what we do is that what we call tokenization process in this autoencoder model. So essentially what you do is not really, Nick, you can't really essentially design a bipartite graph. You don't work with bipartite graph. That's a problem, essentially, because what you work with is this encoding models where you tokenize your information, and essentially what you are left with is that you are somehow putting in, and that's why I was referring to hypergraph or like manifolds, at least. I mean, it's ill-defined here. I'm sorry for you to hear that, because you are mathematicians, and so you essentially what you are dealing with here very often is not bipartite representation of the papers. Is essentially for each paper you have set of so when you tokenize information is a set of numbers that are tokenizing information. And how they tokenize it, there are millions of ways. There is hierarchical tokenization. Tokenization is basically encoding, and it doesn't lead to this bipartite representation. So it can lead to this high order representation, but that's why these methods are essentially interesting. And with recent also papers on the self-regulation of this in this high order space that you get of a projection, I have a sense that people need more on the also understanding of what structures, tangible structures this can be tackled representing, because often we don't really know. Yeah, but thanks for the inclusive. Oh yeah.
Yeah, I think maybe I can do a question because also so I think maybe clarifying Nick's question here. You mentioned you wanted something like invariance and maybe use metric in sort of broader sense of some quantitative measure of your hypergraphs. As you mentioned that you wanted something that was invariant, something can be attributed to the network. So of course, something like a distance or a proximity property would be that. But I think, is it right to say that you wanted maybe possibly something more general?
Yeah.
Okay. So what are you imagining? Like, what are the kinds of things that you want to get in this sort of way? So what are I think Nick referred to distance and length properties and things like that.
Yeah.
What are similar things that you're thinking about that we might help sort of formalize it?
So for example, what we
Luba, you are muted.
Okay, so what already I tried to indeed to point it out, but it was very brief. So I moved the slide very, very quickly. It was essentially that when you apply this set of measures, when you're embedding your information, and the reason why you embed information in the first place was because usually the amount of information is huge and there is a lot of redundancy to represent, for example, text as a point in 1 million dimensional space. So you usually embed it, right? You usually use some sort of a simplification, right? And people like Carlson and Bernstein would be much better explaining that theory than I do, of course. But then, of course, so first, even if you have the best algorithm that will embed your paper, if your information, your data into low dimensional space, imagine that you found this algorithm, it usually has also a lot of parameterization. So are there any properties of these structures, data structures that would be invariant invariant, what I mean by invariant, it's also ill-defined. I'm sorry for the using of the words not properly defined here, but in a sense, an invariant that if you are, for example, applying a set of hyperparameters of these methods, this is the first set of hyperparameters of this method, and you're getting one hypergraph that looks like this, and another set of hyperparameters of this method leads to your embedding, which gives you another hypergraph, like a bit different one. Is there anything universal that you can say that you learned about the structure that will not change? Because essentially it can be a good measure. Sorry, then it will be a good. That it will be a good. Sorry. Really? No. Okay. Yeah. So that was, for example, that is something that is a question typically that is there something that will be a good measure to look at across its hypergraphs, because usually when people get a hypergraph representing their data structure, they're extremely happy, but then they very quickly get disappointed that, oh, in fact, there are not really good measures that would be measures to characterize something very universal, independently from, for example, method that you are or hyperparameter set that you start with to construct your data. I don't know if you answered your question, Carlos, but
maybe just a follow-up question. So, from the end of the day, when all said and done, how does what you call a metric on hypergraphs look like? Is it composed of comparing properties of hyperparameters, or is this data when it is not
yes
of the distance measure?
Yeah. So usually, I mean, first of all, it's not. It needs to be, as Richard said, that one needs to first talk about the distance that you define a pairwise between 2 points. Yeah, the 2 points, and usually you would either, for example, define it as a shortest path on this line graph, right? For example, and that would be one way to estimate it, for example, right? To define it.
But just to say,
yeah, no, but I mean, you take all the paths, then afterwards you find the one which you will minimize.
No, so
unless you
know which is shortest. You already know the distance.
Yes, that's true. You need to define a distance. Yes, you need to construct.
Because in graph theory, at least, there's a very good classification of properties that you can ask about, which are first order. They typically speak about neighborhoods and counts and stuff like that. And then there's one second order where you can ask whether 2 points are connected, for example. Not speaking yet about any distances, but I'm wondering, so essentially what you call a distance measure of some sort would have to be constructed apparently, if I understood correctly, from some algorithm you can perform that somehow explores between, because I can see on one graph how points on a single graph and they give you some notion of they connected to the same components. Let's say you count the number of edges I have to traverse. Yes, maybe there's a window, even though it's not like the graph is here. But if I compare two graphs, it seems up a little bit there is joint. So not the one connect, and it seems to have to do something which dangerously looks like rewriting, because I probably have to transform one graph into the other. First of all, make a connection. Now, that conglomerate, then maybe make counts. But I'm not seeing how it's varied between two graphs. I mean, that seems to be quite a difficult task. How can I even compare them? I can imagine the images and do some
iterations.
Say, but is that what you're doing, or what exactly are you doing?
So first of all, when you have to, for example, hypergraphs like just the ones which we design, we get as a representation of our of our data, for example, and you usually want to have a sense of distance between any of these 2 points, just because it's quite useful in this case.
The same graph, or
So yes, so no, so there are two things. They are distances on the same graph, indeed. So all distances, all pairs. So basically, you are designing. Basically, you're calculating the distance, pairwise distance between all points on the same graph. So on the same hypergraph. Yes. So yes, you have. Yes. And then afterwards, you also want to see if you actually designed your 2 hypergraphs corresponding to the same data set, right? But these 2 hypergraphs are designed using different hyperparameter set of your algorithm, whether there would be any way, right, also to compare them and not to compare. This, okay, then I did not understand your question. And it not
you just make a statistic of, for example, distance distributions.
Yeah, and that's what you do. Yes, and I was asking you as mathematicians, right, as is if
For example, we have this problem here. This is called evolution. There are skeletons and there are all animals. Then you can ask which animals are close to each other. Then you discover some criteria. A mouse and an elephant. It's closer than a mouse and an equal size fish.
yeah.
See that little things are closer and big things are not. But this distance, to define such a distance, we need some criteria. You can say that all triangular structures are closer to each other, and that's quadratic, and so on. So distance is a very arbitrary thing. It's helpful just to have 2 inequalities.
But on the other hand, nowadays you would probably not even bother to, not in many cases at least, to even find something by hand. You would probably ask for a training set and then put this into a graph, right? Or see if things get a bit similar. So, I mean, I'm just saying that probably that's the most difficult part of your project, not to find a good notion of distances from hypergraphs.
Yeah. I mean, also
other than the one can guess, yes.
Also because as a previous speaker also was mentioning, that often people, what they try to do is to apply kind of measures from the I don't know, the generalized version of the Laplacian, or like something that you're usually doing in the graphs case. So it's not something that necessarily will be the best. I mean, they basically first project it into a graph, and graphs are typically usually more studied, and there you can maybe make sense more out of that. But essentially, maybe I cannot answer the question of whether there is also, it makes sense to by comparing these 2 hyperparameter sets, I mean hypergraphs that are constructed different using hyperparameters set of features, which I showed you on this slide, whether they lead to kind of the same hypergraph structure. Because actually, maybe if they don't, maybe then method is doing something wrong, because it just doesn't manage to learn and capture something data, and it's typically something that is a big problem in this community. That people ask me, okay, is it a good method? Well, like, I have no idea, but maybe if you change a bit the set of hyperparameters and it just gives you it gives you the answer to your question which are opposite, maybe then you're choosing not the right set of parameters. So it's kind of helping to construct this method which will lead to semi-supervised manner. Like, you want to explore that set of hyperparameters that will be giving you not such a sensitive question. I mean, it's maybe a bit too machine learning. Yeah, sorry for that. Okay.
All right, so I think we can thank you both again. Thank you very much.